Hello, my name is Caleb Harris, and this is my Lab 5 for Physics 2212, Magnetic Braking with Faraday. Next is Introduction, Physics Principles, and Results. The last purpose was to collect data on a magnet falling through an aluminum tube to observe Faraday's law. The main physics principles are Faraday's law, Lenz's law, and the Bob-Savart law. The results are that the experimental time was 1.25 seconds, and the computational time was 1.18 seconds. And you can see both the Faraday's law of induction on the right with the picture that I have, and on the left with the Bob-Savart law. Here are my models and assumptions. For assumptions, I assumed that air resistance on the falling magnet was negligible and that gravity and the magnetic force from the aluminum tube are the only forces acting on the falling magnet. And the models included a magnet was used to model a magnetic dipole, while the aluminum foil modeled a tube through which it fell. For my system, the surroundings, initial conditions, my system was the magnet and aluminum tube, and the surroundings was everything else in the universe. My initial conditions are that my mu was 2.21. This is calculated from Lab 3. The bar magnet and the magnetometer on phone are also my other initial conditions. And the experiment was using the magnetometer on my phone. I marked the North Pole of the magnet. Then after setting up the camera to record, I dropped the magnet through an aluminum tube 5 times. I then used the video footage to calculate how long the magnet took to fall through the tube for each trial. Here are my observations. You can see in the table on the left, for trial 1, it took 1.27 seconds for the magnet to fall out. For trial 2, it took 1.21 seconds. For trial 3, 1.33. For trial 4, 1.22. And trial 5, 1.22. And the average of 1.25 seconds for the magnet to fall through the tube. And on the right, I have some of my initial conditions of the materials. The length was 0.03 meters, the width 0.006 meters, inner radius of the tube 0.024 meters, outer radius was 0.03 meters, and I have my mu and magnet mass as well, and average time through the tube, like I said earlier in the table. This is my initial code of just initializing the variables, such as the mass of the tube, the length of the tube, as well as like delta T, gravity, and resistivity. That's all this first part of the code was. It allowed us to create the tube. After creating the bar magnet, code was written to calculate the magnetic field and magnetic flux due to the dipole. I also want to include that this is where I used my mu of 2.21 in lab that calculated from lab 3 in this part of the code. After this, the gravitational force on the magnet and magnetic flux on the ring due to the falling magnet was calculated. This was used to calculate the current through the tube. I also want to point out this relates to Newton's third law of motion, talking about how the forces are equal. This allowed me to find out the gravitational force as well as the magnetic force acting on the falling bar magnet. The total net force was calculated by summing the gravitational force and the magnetic force. The velocity was calculated using Newton's second law. Here's my model on the left, and then my graph for the velocity and time. For the model on the left with the magnet falling through, the red ring represents the North Pole while the blue ring represents the South Pole. For the model, the magnet was in the tube for 1.118 seconds. This was a little bit faster than the experimental time of 1.25 seconds. And I do want to point out that in the velocity time graph, you can see that the velocity plateaued at around 0.2 seconds. This is around the time when the gravitational force and the magnetic force were equal to each other. Here are a couple interpretations. Red corresponds to counterclockwise, and the blue the red arrows corresponds to counterclockwise, and the blue arrows corresponds to clockwise. The system was flipped; it would not change the magnitudes of the values; rather, it would only impact the signs and the directions. The computational time in the tube was significantly faster than the experimental time in the tube. My computational time was 1.118 seconds, while the experimental time was 1.25 seconds. And finally, the shape of the velocity time plot shows us that the forces are not initially balanced. However, the forces balance out at the plateau. And this is what I said in the previous slide, how the forces, when the forces of gravitational force and the magnetic force are equal at around 0.2 seconds because the velocity was constant. Here's some sources of error and discrepancies. The main source of error could be that the foil I chose was not the correct thickness, and that I could have incorrectly timed the magnet's drop through the tube. And more than likely, there are no discrepancies as the bar magnet's magnetic field models that of a magnetic dipole. My what if question, if the resistivity, for my what if question, the answer for that, if the resistivity was reduced as close as possible to zero, the forces pushing upward would stop the velocity of the magnets in the downward direction. And for the what if question, for the second what if question, if holes were cut in the tube, it would disrupt the flow of current through the tube. As a result, the forces responsible for decreasing the speed of the falling magnet would decrease. To conclude, the Bob-Sarbat law and distance dependence can be applied to bar magnets with accurate results. Bar magnets can be used to accurately model magnetic dipoles, and understanding Faraday's law is important to understanding how magnetic force impacts the system, which includes the initial force and flux and the response force being Lenz's law.